If you don't have the note guide, you'll just want to write down our data and what we're doing with it. So we're still looking at quadratics. How do I know that I'm looking at a quadratic being the people that collected this piece of data? Why would I feel like this data falls in the family of quadratics? Brandon? Good. So when we're throwing the ball, if we look at the toss of the ball, the way that it travels is like a parabola, right? So this happens a lot with lots of different motion things that are moving forward or going up and down. So because I performed the data, I understand that it should behave like a parabola, which is in the family of quadratics. So now here is our data. So we have a 2458 point. We have 4889. 9694. 12092. 14465. 18017.5. Yep. And then the one I was reading upside down, which is 192.6. Yeah, right.
That 180.
Uh-huh. It was at the 168 mark? Oh, okay. And then this one was at 222.1 because they went 6 inches further than the 18. Okay. Yeah, now. Yeah, we don't have one. I have a piece of data. Maybe that was yours, Brandon. Okay. All right. Oh, yeah, but it's in centimeters, so we're just going to leave it out for right now. We could convert, but we're not going to right now. All right. So we have this data. It's okay that a piece of data is left out. Our data also has some inaccuracies because we collected it. Sorry, we're all human. And our line of sight when the ball crossed and trying to measure that exact point, we probably made some errors. But we should at least have something that we think behaves in the manner that a quadratic behaves, meaning behavior where we see it rising at a certain rate and then kind of turning around and going back down. So we're going to look at this in the calculator. So this is going to review skills from the last unit. We're doing the same thing we did when you guys did the licorice stuff. We're collecting data, right? We're now going to put the data into the calculator. We're going to look at the scatter plot, and then we're going to run some regressions and interpret those. So if you have a calculator, take it out. If you don't have a calculator, you can borrow one from the back. Make sure we at least have one side by side for each pair of people. All right, so while my calculator is loading up here, where do we go to enter data into our calculator? This isn't changed. Okay. Maddie? Good. And which part of the stat? Good. So stat edit is where we're entering data in our calculator. So stat edit. If our list have stuff in there that we want to change, we press clear, not delete, and press enter. So clear, we're pressing clear on the list name and pressing enter. Otherwise, you can just type on top of the data that's there, but then you have to delete the other pieces one by one. 98? Okay, awesome. We'll include that in there. All right, so we're going to go ahead and enter the data that we have. So we have nothing for 0, so I'm not going to put 0 as an x coordinate. Okay. But then we do have measurements at all the other inch marks now. So we'll do 24, 48, 72, 96. So the same data you had in your data table, putting in all the x values, and then I'll put the y values that go with them. What's that? Yeah, it's the data that we all got. And I know we didn't write something down for 72. We figured it out, so that's what we're putting in there. And then remember, the last one's not 216. It was measured at a distance of 222 from the thrower, so make sure that you have that data accurate. So, yes. 222 instead of 216. Okay, so for 24 inches away from the thrower, we saw the ball at a height of 58 inches, 89 inches. Sorry, Brandon, you said 98. Thank you. So our 72 will be paired with 98. 96 was at 94. 120 is paired with 92. 144 with 65. 168 with 17.5. 192 with 6. And 222 with 1. All right. So once we have data in the calculator, how do we view a scatter plot of the data? Yeah, Rasmus. Good. So a lot of you guys just press graph and you expect the calculator to know that you want to see that scatter plot of the data. That's not how it works. You have to turn a scatter plot on in the calculator, okay? So y equals has the word stat plot above it. So those are where all of our plots of our statistics are, of our data. So we go second y equals, just like he said. Go into one of the plots. You would need to turn it on. You would need to make sure it's a scatter plot, which is that first type. My lists are list 1 and list 2, depending on your calculator. If your calculator doesn't have a list 1 because it was deleted or something, make sure that you're using the appropriate list 2 or list 3 or anything like that, okay? Now when you press graph, you probably still won't see this. 98. Okay, so I press this. This is not the graph of my data, okay? This is the graph of a parabola I was graphing yesterday, okay? If I go in my y equals menu, I can see why that's showing up because that's from yesterday's lesson, right? My plot is on. I'm not doing anything wrong. What should I do if I want to see my data? Why am I not seeing my data, Jonathan? Not calculate. That will give us something when we want to figure out an equation or something like that. But as far as my window and seeing my data. Good. Okay. You can set your own window based on the data, or now that you've turned on a plot, you can tell the calculator to zoom to your data that's in there. So we go to zoom right here. And when we're doing statistical stuff, we want to use the statistical zoom feature on the calculator, which is choice 9. Oh, I went too far. Okay, so you should see choice 9, zoom stat. That's what we want. All right, so there's our data. Okay. Not perfect, but somewhat what we expected, parabolic looking-ish, right? So there's a scatter plot. Now, if I want to build a model for this data, to build a model means to find an equation that best represents the data. Okay, like a line of best fit, but now a curve of best fit. Okay? Where do I go for the calculator to run regressions to build models of my data for me? So I want the calculator to come up with the best curve that matches this data. You did the same thing with linear regression. Good. So back to stat. This time over to calc. Now, in the previous unit, we ran linear regressions because our data seemed to travel like a line, okay, like something that was constantly sloping upward or downward. This data tends to act like a parabola. Which of the regressions do we want to run? Good. Quad reg, because that's saying run a quadratic regression, okay? So I'm choosing choice 5. Now, again, old versus new calculator software. If you have a newer calculator, it's nicer in the fact that it gives you a bunch of menu options right now. So it asks for like your X list, right? Your Y list. We don't care about the frequency thing. We leave that blank. But where it says store, reg, EQ, if you want to see your regression equation on the graph without retyping it into the Y equals, we want to put Y1 or Y2 or Y3 or something there so that it copies the equation into that spot. Okay? So your X list and your Y list should match whatever you had in the stat plot as your X list and your Y list. And then remember where to get the store regression equation. I'll show you in just a second. If yours is like mine and it just does this, you just need to tell it your X list, your Y list, and where to store your regression equation. So I need to say L1, which is this blue writing right here. So second one, a comma, L2, because that's where my data is. Then another comma, and I do want to store my equation. So either you're where I am right now, or if you're on the newer screen, you're at the spot that says store reg EQ, and we're going to go get that Y1 or Y2. It's in the vars button, okay? So vars over to Y vars. We only do functions in this class. We don't do parametric or polar, okay? And then there they all are. Pick one, and then press enter. All right, so notice it gives you an A, a B, and a C, and it says your equation up there is ax squared plus bx plus c. So our equation is that y is equal to negative 0.005x squared plus 0.816x plus 55.971. Does it make sense that the a value is negative? Yes. Okay? The a value should be negative because we would expect the parabola to face downward. Okay? So just these things, the things that you know about parabolas, you know how I was talking to you guys yesterday, like technology can do a lot, but you don't want someone operating the technology that doesn't understand what they're doing. These things that you know about quadratics, like they should make sense when you're finding out this information. Okay? All right, so let's leave our calculators where they are right now and look at the questions that were asked about the data. The scatter plot, you guys can just sketch them from the window of your calculator for anything that we do on the calculator. This gives you guys directions. So if you're having a hard time with the calculator, you could highlight these directions right here. Obviously, all the notes are recorded, so you could go back and watch the keystrokes. You can also just Google, and lots of people have different little instructional videos on how to do this stuff on the calculator. And then we want to answer these questions. All right, so we got the equation. So for number 4, sorry, it skips number 5. So for number 4, you want to write down the equation that we got. Okay, so that y equals negative 0.005x squared plus 0.816x plus 55.971. So the question. So question A says, what is the y-intercept of the graph and what does it represent? So how do you find the y-intercept of the graph? Plug in 0 for x. Okay, and it's written in standard form, so even though the numbers are super crazy, all this stuff is getting multiplied by 0, all this stuff is getting multiplied by 0, and then I just have this thing at the end that's not getting multiplied by 0. Yes, so I get that y is equal to 55.971. So my y-intercept is the point that when x is 0, y is 55.971. What does it represent? So when problems have context, the y-intercept is not just a number anymore. The y-intercept tells me something about the scenario that we just performed outside. Brandon? Good. So that's the height at which Jeremy was holding the ball, okay? Or the height at which he let go of the ball. Does that make sense to everybody? Because he was standing at the 0 mark. That's the height that the ball was at 0. Because this literally means, remember, our x represents distance from the thrower. So at a distance of 0 from the thrower, the ball was at a height of 55.971 inches. Okay? So this is the starting height of the ball, the height that it left Jeremy's hand, how he was holding it at 0. All those would be acceptable answers for what this represents, okay? So this should be very similar to what we did with linear stuff. We're just using a quadratic instead, okay? How far from the thrower did the ball reach its maximum height? Now, we don't go back to our set of data for this. We have one piece of data that showed us the maximum height, but we didn't have millions of us all minusculely small marking the data along the way. So we're using our model to answer all of these questions. So we need to let go of the data table for a second because it has errors and different things, and we need to use our model to represent this. So how are we going to find how far from the thrower the ball reached its maximum height? Jonathan? So look back at your calculator visually. Which part of the graph represents the ball reaching its maximum height? Natalie? Good. The max of the graph represents where the ball reached its maximum height. So remember, on the graph, we can find the max by going second, calc, and choosing maximum. This will find the vertex for us. So then we have to do what we did yesterday, left bound and right bound. So I'm going to the left of the maximum. Okay. And press enter. I go to the right of the maximum. Press enter. It says guess. All right, so I get this vertex point, 78.27, 87.91. So now we need to interpret that correctly when we look back at our question. We found the vertex. (78.27, 87.91). We know that our data went higher, but remember what a model is. It's generalizing the data, because in general, you wouldn't do this for one person's toss. What you would do is you might have Jeremy sit there and throw the ball 50 times. And you'd plot all that data on one scatter plot, and then you would try to make some general statement about how Jeremy throws the ball, right? Which seems kind of silly in this context. But let's say you were launching something and trying to hit a target or something like that, okay, like my intro students do with their catapults. Well, they take that same data, but they launch it tons of times. Then they get the best model that represents their data so they can decide how far away they should set up their catapult, depending on how high the barrier is that they're trying to get over, and different things like that. Okay? So we don't use the specific data because usually it's collected multiple scenarios of data, and so you don't want to pick out one specific thing. You want to look at the overall trend of what's happening. Okay? So this is our vertex point. So what answers the question? How far from the thrower did the ball reach its maximum height? Natalie? 78. Good. 78.27 inches. And then part C says, what was the maximum height that the ball reached? What's the answer to that question? Good, 87.91 inches. So not only do I have to be able to find the vertex, but I have to understand it in the context of the problem to interpret the information correctly. This isn't just a random point. This is telling me this far away from the thrower, the ball was at that height, and because it's the vertex, I consider that the maximum. Okay? How far from the thrower did the ball hit the ground? What would we want to look at for that? Brandon? Good, the x-intercept. So our problem definitely has some limitations, right? We see on the graph the parabola going below 0, but would that ever happen in our scenario? No. That doesn't mean we have a bad model. It means we only use the model in a certain area, and then there are limitations to when it's good and when it's not good. So let's look back at our calculator to find that intercept, like he said. And so I'm going to go second, calculate, and I'm going to choose choice 2, 0. And then we're going to find a left bound and a right bound. Sorry, lots of scrolling here. Okay, so left bound here is like above. And then to go further to the right, I have to get below. Now, if you can't see on your graph if you're below or not, pay attention to the numbers in the window. Am I below at this point? No. My y says 2.3. That is above the axis still. Okay? So I go again. Now y says a negative number. So I might not be able to see it, but at least I know I'm down there. Okay? I have it guess. And so I get this. So look at the y value there. 1.2 e negative 11. Do you guys know what the e means on the calculator? Scientific notation. So this really means 1.2 times 10 to the negative 11th power, which means move this decimal over to the left 11 times. So it means a decimal with 10 zeros and then a 1. Can we call that 0? Yes. Why does it turn out that way? Same thing we talked about yesterday. The calculator is performing a calculus algorithm to figure these things out based on the points that you pinpointed. So it might sometimes not come up with an exact 0. Or like last time we saw 2.9999999 and we called that 3. Okay? So if it has a lot of 9s or a lot of zeros, you can round to that whole number that's right there. Okay? So this is at the point 208.12, comma 0, basically. So 208.12 was my x coordinate, right? That was inches from the thrower that the ball was reaching that height of 0 or hitting the ground.